So this is just meant as a backdrop, so you don't have to read it all. I think the main message is that for my entire kind of career, I've been kind of into languages and systems, worked on many different languages, worked on many different systems. For the past several years, I really moved into engineering management. So many of the things that I've been listing here more recently, in particular data like analytics and U-SQL that I'm talking about today, are really not the fruit of my immediate labor, but the fruit of many, many other people who have been working on these things. The other thing I want to make sure is that, although it may come across like that, I'm really, really less about promoting particular Microsoft technologies here today, and more about talking about particular ways of thinking about how to deal with massive data and the opportunities that you really get when you do analytics over big data. So this is one of the most recent XKCD comics, and it describes the situation pretty well. For a lot of people, analytics over really big data ends up being kind of a black box puzzle. Many of you, of course, are into this. The actual conference was full of particular talks about various aspects of that. So take it with a grain of salt. But in general, I keep finding that when we look at the explosion of data that we have been seeing over really just the past decade or so, the fact that I actually in practice start talking about things in the exa and approaching zeta scale blows my mind. When I studied electrical engineering, these things existed and were used to measure kind of extraordinary things in our universe. Like, for example, the lower estimate of stars in the universe is in the iota range, right? Or the number of cells in the human being is in the exa to zeta range. Number of atoms in the human being is like 100 iota range. So these are numbers that are astounding, and yet we're now starting to put byte behind many of these things, right? And we think now mega and gigabyte isn't even worth mentioning anymore. It's such tiny amounts of data. Terabyte, we almost jumped over that, right? It's like, oh, that's just one hard drive full of stuff. We easily talk about petabytes and exabytes these days. And for good reasons. There are many systems and many application areas that just produce that deluge of data. The only question is, what the heck do we do with all that data? So this is kind of a picture of where all the data is coming from. And you can actually see all the way to the end of last century, really, analog sources were a primary source of data. That, as you all know, has been effectively disappearing. So we're all in a digital age right now. But now the internet-connected world, Internet of Things and other such phenomena, is really creating the next, even more massive wave of data. And it's not just Internet of Things. If you, for example, operate a major website and all you do is analytics over your clickstream data, then you're also already dealing with astounding amounts of data. So while we are effectively driving the production of data forward, we are also beginning to see increased value of data. There are now ever more companies that, as their primary or even only business model, sell the data that is almost the exhaust of what they appear to be doing. Right? So you go to a company, operate some free website that does something, and what they're actually doing to make money is selling the data that they effectively gather, and usually it is the data that can be correlated with other phenomena, right? So for example, if you can predict certain things based on the data you gather, then that data becomes that much more valuable. If it's just for raw data, we all have plenty of that, right? So before you know it, you also hit the range where doing machine learning, various other forms of AI is suddenly exploding all around us, because that's one of the few ways of actually extracting true value from the sheer amount of data. So before I go into any specifics around what our products do here, just want to give you a quick insight. Some of you may have seen those things before. So inside Microsoft, we have a system called Cosmos. You heard about Cosmos DB, by the way. Cosmos DB and our internal Cosmos system are actually unrelated. We just like that name. So the internal Cosmos system is effectively a collection of super large clusters that run a very large part of the Microsoft business. And just to give you an idea, these clusters run in the hundreds of thousands of machines, millions of cores, petabytes of RAM, exabytes of disk space, in fact, probably tens or hundreds of exabytes of disk space. And that actually is only an internal used fraction of the overall Microsoft cloud. So it's actually not even dominating the space, but it's a very large system. So just if I could ask for a quick show of hands, who has actually worked with clusters that have 1,000 machines in them? Okay, a few people. Who has worked with clusters that have, let's say, 4,000 machines in them? All right, so very few people now. It turns out that many of the current cluster technologies actually stop scaling at around 4,000 or 5,000 machines for various architectural reasons. The clusters we're looking at here have on the order of 50,000 machines in them, and there are many of those clusters. So pretty massive stuff. This, of course, hasn't come together overnight. This is the result of about almost the past decade of work. Some of that work came out of our research branch, and you may have heard about it. There's a system called Dryad, including kind of a link attached for it that was published, I think, in 2001 or 2011. Sorry, 2011. Dryad was also one of the foundational things that inspired Spark. So there's quite a bit of long-term work behind all this. And then a few years ago, we really set out to say, okay, if we can do all this stuff internally, right? And some of that runs in near real time to, for example, do reporting for Bing Ads customers, publishers of ads. Some of that runs in less real time, and it's about figuring out whether, for example, the latest push of an update in Windows or Office is having unintended side effects, like someone's machine having trouble. So we're basically looking at all that telemetry data coming back and using machine learning over that to look for signs of trouble. So with all those systems in place, we really wanted to go and if you like, productize this. And so we, about 3-4 years ago, started with an effort that now led to a thing that late last year hit the market under the name Azure Data Lake. So there's an Azure Data Lake Storage and Azure Data Lake Analytics. Those two services together effectively reflect what our internal Cosmos plus Scope system does. And basically, it is the first dip in that space. So we'll actually keep expanding what this product does to a large degree based on what we know from our internal systems. So that's just as a backdrop. And I can tell you, just the sheer numbers, you don't get used to them. It's like the numbers blow me away every time I look at them. By the way, an interesting thing here in the bottom right, I'm not sure how absolutely current this is, but the Congruent guys declared a 4 commas club. The 4 commas club is, so there's actually, in the real world, there's a 3 commas club. That's people who have $1 billion or more. Okay, so it's a very elusive, exclusive little club. And for Kafka, there's now a 4 commas club. That is operations that use Kafka at 1 trillion messages a day rate. Okay, trillion a day. And as you can see on this list, I haven't seen a newer one. We have Microsoft and LinkedIn, which is now part of Microsoft, be 2 of the 3. Right? So we're definitely also massively in the business of taking a lot of data in. Talk about other things. I wanted to give you a quick idea how some of these products look. So here is a little kind of, this is really not a real website. This is a little fake dashboard that we put together to just show one particular flow. The real flow behind that is actually something we have actually built where, so imagine you have a customer support organization that builds call logs, literally transcripts of whatever customers who decided to contact customer support had to say and what the responses were and how the dialogue went. And if you now take this data, which is like really only in the hundreds of gigabytes over a number of years. So this is old style data, right? It's not very big. You combine that with social media data that you can then time correlate. You combine that with system health data, various forms of telemetry that again you can time correlate. And you combine it with machine learning, then you can do sentiment analysis over customer support situations, right? And you can actually go and say, even at a statistically relevant level, how does my larger customer base react to what's currently going on? So this system, for demo purposes here, I have, all right, actually I'm not connected right now. Which probably means I have to type in that endless password, right? Any suggestions which one I should use here? Auditorio. Okay, and let me see. No password? Ah, that's nice. All right. So what we're looking at here is the Azure portal, the management portal that you use to manage all of your kind of deployed Azure services. And what should show up here in a second is the statistics of an Azure Data Lake store account that we really assembled for this particular demo. And that has about 2.2 petabytes of data in it. So that's what you now see here. This particular one is holding on the order of maybe 500,000 files that are in the 5 to 20 gigabyte range. Okay, so the individual files are not super big, but the number of files in total is like takes you into the petabyte range. This particular store equally happily operates over single files that are petabyte sized. Right? So it's actually intentionally built as a file system. It looks like HDFS, has a POSIX ACK-link semantics on top of it, so you can attach lots and lots of existing systems to it, but it has practically no limits on the number of files, on the size of files, on the bandwidth to those files, exceeds by far other systems. So this was specifically built to enable big data analytics. And just one, all right, so let's hope this refreshes in good time. This is actually a preview of one of the files which shows you all right, let's just open any one of them. So that just shows you the first few rows of a 12 gigabyte or so text file. And you can't actually read this. Projector doesn't like the resolution, it seems. So what you're seeing here are individual log entries. And the last column is just free text. Okay, it's just whatever the support specialist ended up typing into this particular log entry. So looks like I should have connected to the network before. All right, maybe this is a VM that has a few things in it. If you can't connect to that, that's not the end of the world. Let me just open this here. So what we're seeing here, this is actually out of our own live telemetry pipeline that is looking at consumption and billing and health and other things of the Azure Data Lake products. And what you see here is one particular job. And I'm just going to read a few things to you because that, you really can't read that. So this is a job that ran on a total of about 8,000 what we call vertices. A vertex is effectively a container that has a particular physical resource allocation. So you can think of it as indeed as a container or as a VM or something. So about 8,000 of those that were sequenced over time. And what we have here at the end, what you're seeing here is a playback. You see this little thing moving down here at the bottom. This is now an accelerated execution. The job ran over a total of 2 hours and processed 1.7 petabytes of data. So this job, as you can see, is now executing. And what this tool actually does is it allows you to actually relive the execution of the topology that we built for you over time. So you can now, for example, go and say, are there any problems with this? And so the system goes and checks whether the execution of the entire job looks regular or has some problems. And for this particular one, it says that it noticed some problems with data skew. Right? It's a fairly common problem if you balance distributed computation over a particular data sets and you basically align compute workers with data partitions. If your partitions aren't roughly of the same size, or the work for each worker isn't roughly of the same size, then you may find that some workers become the long pole in your execution, and the next stage may even block on that. Right? And so this tool actually allows you to find out what's going on and goes as far as pointing you back to some online recommendations for what to do if you encounter data skew problems. Right? So that's a very real loop that as a data engineer, for example, you would participate in. Now the interesting thing here is, if we go back to this particular job graph, let me see. How do I go back here? Strange. Oh, my bad. So what the job graph is really showing you is, and I said that we built this for you, what the job graph is really showing you is how this particular piece of work, that job, executed as a graph on many, many machines. By the way, not every of these green boxes stands for a single machine. If you have a whole fleet of machines effectively running in parallel on the same logical step, they show up as a single green box. So some of these boxes may stand for hundreds or even thousands of machines working in parallel. So, but what this really reflects is kind of the logical graph that we built based on your job description. And if you look at systems, many other systems in this space effectively force you to build those topologies by hand in code. Right? So this system here goes and computes the topology for you and optimizes it globally based on not just your input, but also on the statistics on the data side. So if you want to leverage data at that kind of level of magnitude yourself for whatever you want to do, right? You're running your own company, you're working your own company, you're offering a service, then really there are very few options you have, right? Unless you want to be in the business of operating globally distributed data centers everywhere, then going into a public cloud system is actually really almost the only option you have to leverage that kind of data. And of course, Microsoft is offering only one of those cloud platforms. So if you look at, let's skip over this one here. If you look at the public cloud space And I'm sure you have all seen this. Even this particular picture has been around for a while and has been used by many. You really see this kind of like shift of how much responsibility for the overall stack, if you like, you're willing to surrender to someone else in exchange for some benefit. Right? And so on the left, you're saying, hey, I'm running my entire thing on my own premises and the entire stack all the way from the hardware plugged into my power to the top-level applications. It's all mine. Right? If you move into a cloud system, the easiest and kind of least lock-in step, if you like, is to say, I'm just going to take compute, storage, networking infrastructure in someone else's data center, and I'm going to build my stuff on top of that. But I'm bringing my own operating systems, my configuration of operating systems, my own middleware, my own everything, all the way up the stack. Then you can move on from infrastructure to platform as a service, and you say, okay, no, I don't want to worry about operating systems and their patching and so on. We all just saw where that can lead, right? Last week or so with the WannaCry attack. The biggest problem there was that tons and tons of operating systems in the world were not at current patch levels. So we go and say, no, I don't want to worry about this. I'm going to move all of that also into someone else's hands, and I'm going to just build my solutions on top. And finally, you can go as far as having your entire solution as a service or software as a service. Right? So this is a scale that you can think about. If you really want to think big data in the sense of big that I mentioned today, then the on-premise solution is effectively out for almost everybody. I mean, there's still a few hundred companies around who play in that space. Many of them are actually looking to get out of it. And then you can go and say, well, maybe infrastructure as a service is what I want to do. I'm going to just spin up clusters of VMs and manage everything on top of that myself. And if you have ever done that, I can guarantee you this is not really fun. You really want that problem in someone else's hands. It's a little bit like going and saying, hey, in the old days, I would just build my own Linux instead of going with a standard distribution. That was fun, but it's probably a bad idea for most of us, right? Instead, we pick a standard distribution where we know that all the pieces have been tested, they're all moving forward in time, they all work together. Same thing here. So you quickly move yourself from infrastructure to platform as a service. And at that point, I would actually claim you're unavoidably attaching yourself to one or the other vendor. So instead of thinking about this lock-in phenomenon as a bad thing, think of it as, if I want a really good product, I end up locking myself to that product because I'm going to take advantage of it, right? So there's a common meme, if you like, going around of, hey, I want to run on all possible public clouds. And that often pushes you back down to all that I can do is have raw storage and raw VMs, and that's basically what I have. So just a thought. So if you go and look at the platform level, you actually are exposed to a whole range of trade-offs. And if you pick the right point, so to speak, you can gain hugely from these platform as a service layers. So here's a whole kind of laundry list of these things. And although I have a slide for every one of them, I'm not going to spend too much time on these guys. But you can imagine if you, for example, look at the data lake stuff that I'm talking about today. If you allow petabytes to exabytes of your data to live in such a data lake, you better have pretty high belief that that data is in good hands, right? That it, for example, meets your own regulatory requirements. So if you, for example, have data that isn't allowed to leave the European Union, as an example, or as you probably can hear, I'm from Germany originally. Germany has particularly strong laws around where the data that is kind of operationally in Germany can go, and if in doubt, it has to stay in Germany, right? So if you think about that, if you think about the need to meet all these regulatory requirements, you need to look for platforms that actually have support for all of that. So this basically builds a checklist for you to actually go and say, okay, these are the things that I need. Who can help me with that? And again, this is not Microsoft alone. I mean, there are alternatives, no question. So let's not go into these. By the way, I will make the slides available. You can look at these in detail later. Here's perhaps an interesting one. When you talk about price, right? Of course, there's always the thing that ultimately when you go and say, hey, I'm going to work over an exabyte of data, and I'm going to run work that spins up thousands of machines for a long time, clearly you'll get a bill at the end, right? Hopefully that bill will be a fraction of what you would have paid had you spun up your own data centers, but still, you'll get a bill. And so at that point, one thing that is interesting is to understand how does the billing model really work. Right, so for example, you could say that at the bottom, you see this concept of I'm running many different activities, and I'm really at a microscopic level exactly paying for what I'm using. Right? You'll actually find that no one offers that model today, at least. Right? So that's what we would call area under the curve. The next more granular model is, and that's what most even elastic systems do, is there's a box within which your activities happen, and that box is effectively resources allocated over time. And while the allocation may vary in certain step functions, you still get a rough kind of boxy area around your actual work. That's really saying if you ask for work that requires at least a VM, then we are not going to bill you for a fraction of a VM. Right? And then there's the top level model where and that's what you usually get when you go and effectively pay for an entire cluster of machines, for example, and then do whatever you want with that cluster of machines, including nothing. Then you're actually paying for the bounding box around all the potential work that you might do. Right? And that, if you're running your own clusters, then you're actually finding that that becomes an interesting thing. Your company may say, we can't possibly have finance operations run in the same cluster where your data scientists run experiments. Bang, now you have two clusters, right? And before you know it, you have several clusters. And then you say, okay, so how can I actually get the most juice out of my clusters? So I carefully look for workloads that can all run together in the same cluster. And then I run into other troubles. So this is an interesting way of looking at how the world is carved up and how you end up paying for it. Another thing that I personally always find sort of important is what are the guarantees that the services actually give you. Dharma, for example, when he talked about Cosmos DB, talked a lot about a high nines guarantee on latency. Right? So if that's something that your applications need, then that's exactly what you want to look for. You may find that you're fine with asymptotically correct results, right? So kind of eventual consistent models. You may find that you need very strongly repeatable results. So if I, for example, talk to our finance guys and says, yeah, you know, the reporting that the company will send out is eventually consistent, right? No way. They want absolutely repeatably the exact same finance results every time. And they want the computation to, in that sense, be auditable and accurate and everything. Right. So depending on what you're doing, you want different semantic properties for the services you're using. And then the next problem up really is, it turns out the whole beauty of platform as a service is that no single service in a platform will solve your problem. Okay, that's the whole point. If it did, it would already be one level higher and closer to kind of software as a service. The whole point is it's a building block, more like a Lego brick, and the actual solutions you want to build need to be built by instantiating and composing multiple such platform services, right? And that unfortunately raises the specter again for all these qualities, right? You may, for example, have two ingredient services that meet all your security requirements, but unfortunately, the way you compose them allows the data to escape unencrypted over the wire or something. And so from a regulatory point of view, your solution doesn't meet the bar anymore, although your individual services did. And so all of these things come back, and you need to, again, ask yourself, under composition, do these things all still make sense? And depending on who you are, whether you're kind of like doing in-house or solution integration, whether you're an independent solution or traditionally we would have said an independent software vendor, so you're building a new platform on top of someone else's platform for further selling. Or you're an independent independent solution vendor, you're actually encapsulating the platform. Independent platform vendor would be you're building a new platform service on top of the existing platform services. The last one is actually the hardest, if you really think about what that means for security and general composition of the platform. So I often get this, and many of you probably likely react the same way. You'll say, hey, isn't that just all programming? Didn't we just learn how to use the Orleans framework to build systems like that? So this is what I actually hear a lot, that people say, hey, it's easy, I just write code, and in my code I go and say instantiate this service, instantiate that service, combine them, do something. And the problem is you can totally do that. There's nothing you cannot do in programming, right? Anything you do this way, you will have to answer all the questions that I mentioned before about the quality of the resulting solution yourself. Right? Your code does whatever it does, and therefore your solution does whatever it does, and you are the only one who knows. Right? And so it actually is useful. Yes, you do want to use languages for composition, but it's useful to think about what kind of languages you want to use. Right? And so here's a little picture that you may have seen. I like showing that, where if you think about languages as just a careful assembly of basic instructions that you can kind of use to build up bigger programs, then you can have very low-level languages that are understood by very specialized audiences, or you can have very high-level languages that tend towards getting close to specific domains that are, again, only understood by limited audiences. And then we have our general-purpose languages, right? That's where the Java, Scala, C#, Pythons, and so on live. Now, it turns out the reality looks a little bit more like this. If you really, really go and push a language into total general purpose, it becomes an enormously large language, right? So for example, I have been tracking C# very closely. I've contributed to it at some point. C# by now is a really large language. I learned it over the years as it grew. If I had to learn it right now, I would actually at least be impressed to really know that language, right? So effectively, you find that languages that voluntarily shift either to lower level or higher level and avoid the complete generality spectrum in the middle tend to actually get a bit of a boosted reach. And a lot of languages arose in that space, right? It's like people even built Facebook out of such languages. Right, so one way to look at that when you look at languages that are more specific is how can you view them in the larger picture, right? And so, for example, for these domain-specific languages, we've been for a long time talking about whether they are internal or external. What that really means is, are they embedded inside a general language or are they on top, right? And so in C#, again, as an example, we for a long time now had this language integrated query pattern, LINQ, which really puts a functional language with more limited semantics on the inside of the general language, right? And you'll see the same kind of pattern, for example, in the APIs that drive Spark, and you see it everywhere, right? Now, if you actually are after truly analyzing what your solution will do and understanding its performance characteristics, understanding its security characteristics, and so on, you do not want the outer language to be a general purpose language, because we simply cannot analyze through that language. So you can flip this picture around and you can say, what would happen if my outer language is entirely declarative and my inner language is general purpose, right? And so that's the design pattern. There are a few languages like that. U-SQL isn't unique in that space. I would, for example, put Hive into a similar category. So here you go and say, I put something that is fully analyzable, like SQL, on the outside, but then I do what SQL itself doesn't do well. I put general computation on the inside. SQL tried to do that, but if you ever go into the space of updatable views or triggers or anything like that in SQL, you'll see, I mean, I personally always say the people who designed that language didn't know anything about other languages. But it certainly, it's not a pretty world, right? So SQL is great if you do data definition and data query, but if you go into the innards of stored procedures, for example, it becomes pretty messy very quickly. So what we did with U-SQL is we said, okay, we like T-SQL as the declarative shell when it comes to data definition, data query. It ultimately builds data flow graphs, like the one we saw before. And then we put C# at expression level and below. Okay, so that's a, at first, slightly jarring thought, but turns out I haven't yet met someone who knew SQL reasonably well who wasn't familiar with U-SQL pretty quickly. So it seems to be not such a big deal. And I'll show you some examples. Here's some other examples of drawing on declarative instead of full programming across the Azure universe. But again, let's just not spend too much time on this right now. In U-SQL itself, you're actually getting a lot of benefits from that declarative outer shell. And on those benefits, by the way, do not come from nothing. There's very serious engineering behind a language that's analyzable. You have to actually do the analysis, right? You have to develop all the optimization heuristics. You need to build all the tooling that makes it, again, possible for you to understand what now happened. One thing that that baffles me is when I'm running, for example, SQL queries against a database that is optimizing, and everything is great. I go into production, and then suddenly, I get catastrophic performance. And I go and look, and it turns out the optimizer decided in this particular edge case that I now finally hit with my overall data stats, for example, it decided to pick a different plan. And while the plan it picked previously was just perfect, this new plan is unfortunately not so great, right? So to overcome that peril, that's always a real threat from systems that are trying to do things automatically that you would otherwise do by hand. There's always that danger, so you need to have excellent tooling to understand what's happening and to guide the system out of such spots if that happens. So one thing we do is we actually run the compiler, the optimizer, the code generator every time a particular job runs. So if you, for example, are in batch mode or in interactive mode, we every time take you through the entire pipeline. And the compiler already is aware of the actual data. So it, for example, says, oh, your data is logically partitioned over, I don't know, because you want it to be ready for massive scale. So you're saying I have 10,000 partitions, but most of them are empty, right? So instead of spinning up tons and tons of workers that sit on empty partitions, we eliminate empty partitions already at compile time. At optimization time, we look at the entire graph and do pretty crazy things, like, for example, pushing predicates up through the data flow graph. That's normal, but we push them even through custom code. As long as your custom code has the right kind of read-only annotations on certain aspects, we can push predicates right through your custom code. So your entire solution gets optimized, although it has islands of pretty opaque arbitrary code in it. And we can even look at security properties of your overall flow, because data cannot just escape somewhere and reappear somewhere else. There's no hidden state in the system. By the way, U-SQL, the name stands for Unified SQL because it unifies these aspects of traditional SQL and full programming. And it unifies a number of other things as well. So we can skip that here. So now if you go and think about extensibility of a declarative language, the easy trap would be to say, wherever you want, code can go here. Right? So that would be the model where you say, I can just call a function wherever I want, and the function can do whatever it wants. The problem is, as soon as that's your model, we'll be able to analyze the pure declarative solution, and we'll immediately drop dead when you have one of those call-outs that go into arbitrary code goes here. Right? So instead, we have a whole battery of separate interfaces that you can pick from. And as long as you implement those in a faithful way, so for example, a reducer, if you implement a reducer, going from n rows coming in to a single row going out, for example, as long as you implement that contract, we make assumptions based on that and optimize right through your code. So that's an important aspect of the system here. So there's a whole bunch of, so actually previously here we have user-defined functions where you really have functions, but they are limited to really the simple point-wise application. You have user-defined aggregates, and then you have user-defined operators, and there's a whole bunch of them. Extractors, outputters, processors, appliers, combiners, reducers. And you know, in the future, if we find more patterns that we can lift up to this declarative form, we may define more of those, right? So this does two things. One is when you implement a reducer, because you're now so specific about the contract, the code becomes very reusable across multiple U-SQL definitions, right? Because it's only now locked to your local understanding of the data coming in and the data going out and the specific point operation you're going to do there, that you can build all sorts of different U-SQL jobs using the same custom code if you want. And so factoring becomes very natural. Here's a little overview of the metadata object model. Let's not spend too much time here, but basically if you know typical SQL database systems, then you know what the meta model looks like. You have tables, you have views, you have table-valued functions. And of course here, we have one thing that is pretty unique. In the top right, we have arbitrary .NET assemblies, but in fact arbitrary resources. So one thing that we happily do is say, hey, the custom code I'm running is actually some R script over an R library. And so now you can run at massive scale, you can run your R code at every point of your data. And you don't have to worry about how did the library even get there, what do we do if faults happen. That's, by the way, as you probably all know here, but most people don't think about it. If you think about thousands of machines doing work for you, you have to assume that something goes wrong. Right? Single machines seem to be pretty reliable. Thousands of machines always show problems. Right? So your entire system has to constantly deal with the fact that something goes wrong. And ideally, you don't want to care about that. It should just continue working, should mask things. For example, the U-SQL runtime uses an anomaly detector on your behalf to actually say, it looks like out of this fleet of machines that are supposed to do something very similar, one of them is falling behind. And so instead of going and allowing that one to become the long pole, we schedule a duplicate of that, run it automatically on our own dime, and say, well, you know, if the duplicate behaves the same way, then it's probably more related to data skew or some other application-specific behavior, too bad. But if the duplicate actually catches up and overtakes the other guy, we take the other guy out and let the job complete in good time, although this machine was sick. And that's actually one of the biggest problems. Machines don't just quit. Right? That's the easy part. If a machine just stops existing on your network, you can detect that and you can route to another machine, you're good. But if a machine just suddenly becomes a little unhealthy, you need a whole bunch of infrastructure to recover from that. Right? And we don't normally just hit the eject button on these machines and throw the hardware away. So there's a whole automated cycle behind that of actually saying, well, maybe if we can just completely clean and rebuild the machine, it moves back into a healthy state. But if it does the same thing again, then we eject the machine. Right? So that's things you don't want to worry about, right? You just want to hope the infrastructure does that for you. So here is an example of how U-SQL scripts look. Let me see, can you actually read that? I think that's reasonable. So at the very heart, you find SQL-like select expressions, where you have all the typical select things. Oops. Then you can build data flow graphs simply by referencing sort of named expressions. And unlike some other systems, if you break your graph into such steps, it stays entirely declarative. Again, we optimize entirely through that. And just because you're, for example, referencing the same expression now from 2 different places doesn't even mean we insist on having a single instance of that. Right? So we completely rebuild the graph for actual physical execution. But you can think of the problem that you're solving nicely as built out of individual pieces that form the data flow graph. So then you can go and say, I'm going to input and output unstructured data. Very common in big data is that a large part of your data is just chaos, like CSV files or even text logs or images or stuff like that. And likewise, you can have relational data, tables, and again, input and output at that level too. Then you'll see the actual type system here is really the type system of C#, right? Not the one of T-SQL. The expression language on the inside is again C#. So if you actually end up calling into user code anywhere, it's very natural because we call expression already as part of C#, and therefore you can do whatever you want to, for example, post correct whatever the called operation returns for your local needs. Right, so you don't have to write some hidden wrappers to fix things. So here we have a case of a user-defined function, user-defined aggregate, user-defined operator. And finally, something that is actually, so this is just telling you what I talked about before. Finally, something you don't see in this example is you can also cause U-SQL to federate queries to other systems. Today, we only do that for SQL sources. So if you're part of your big data solution, you have some reference data in a SQL database, you can just use the SQL database as another data set here. And we recognize that that's a smart source and not just a flat file store, and send calculated queries back there. And if you don't want us to calculate them, you can also just inline the queries you want to use. So you basically get integration with other data stores, and we'll add more of those over time. All right, so let me just skip over these things. You can't really see them anyway. So at this point, I want to stop. We have probably a few minutes for questions, I believe. Yeah.
Any questions from the audience?
Everybody's tired and wants to go to the beach.
Okay, well, thank you very much, Clemens.